is emitted at E, it will be received at O. And then what happens is that if you look only at the linear order in variations of positions, the only thing you see is basically the Ramer delays and the time transfer effects. Basically, if you position your clock closer along the null geodesic, the time of arrival will be shorter. If you put your emitter if you move your emitter to the back, the time of arrival will be slightly later, and the same thing happens on the other side. That's basically the effect of finite light speed. There is no transverse effect at that order. On top of that, note that the rate of change of these times of arrival is slightly different on these two different points, and this is not a mistake. This is due to the time transfer effect, or simply the redshift and blueshift effect between these two systems. But what happens if we take slightly larger regions? Well, we'll begin to see the quadratic effects in displacements, some transverse effects on top of the linear dependence. And these quadratic terms basically are made of two types of effects: the finite distance effects, so something you see in a flat spacetime. Basically, if you send a signal from E, the corresponding wave surfaces will appear curved. But on top of that, there is also an imprint of the spacetime curvature all along this null geodesic. And the idea is somehow to recognize this imprint from these quadratic terms. I will show you how to do it. It is possible. Now I have to go to the conceptual and geometric part to explain how this measurement works. So I have to begin by the product manifold. So the product manifold is basically m times m. So a manifold made of pairs of points. And we've got the pair OE somewhere here. Now we can think about tangent vectors to this product manifold, m and m. That's a big capital vector X. And this thing is basically, if you write it down this way, it's basically a pair of vectors, one of them tangent at the point E, the other one tangent in point O. Basically, you can introduce a coordinate system here. This will introduce some kind of quadratic coordinate system on the product manifold, and you'll be able to write any vector in the tangent space of 2m and m as a block consisting of 8 numbers, a vector at O and another vector at E. So if you like fancy geometric terms, you can say that the tangent space to m times m at O and E is basically a simple sum of the tangent space here plus tangent space there. This simply means that there is a unique geometric way to represent every vector here as a vector here plus a vector over there. M times m has no metric yet, but we can introduce a non-degenerate metric tensor in the following way. We simply take the O part and take the G product. We take the E part of the two vectors, multiply them with E, and we take a minus here. And this gives this thing a geometry of a manifold of dimension 8 and signature 4, 4. This is not completely, this tensor is degenerate along the diagonal, unfortunately, but this is not so much of a problem for this formalism. The minus sign here somehow simplifies the algebra later. It may seem arbitrary and surprising. You could in principle use plus here, but somehow the algebra later becomes simpler if you use a minus. I don't know if there's anything deep about that. Okay, now comes the most important notion of the whole business, something I call the local surface of communication. I've never seen this notion actually defined in the literature about light propagation, which surprised me. So basically, it's the geometric locus of pairs of points which can be connected by a null geodesic. So out of these points, we pick up those points for which we can find a null geodesic connecting them. Of course, this is not true for any 2 points here, but this is true for many of them. And this will be a set here. Unfortunately, the set is never a proper submanifold for 2 reasons. One of them, it's always degenerate along the diagonal. And secondly, typically, light propagation involves the formation of caustics, which will produce self-intersections and various types of singularities of the surface. However, locally, you can hope that this will be a 7-dimensional submanifold of this dimension 8 manifold. Now, this thing is rather abstract, but it's a funny thing because it defines the shapes of all possible light cones you can think of. So typically, in GR, light propagation is defined in terms of light cones. There's nothing wrong about that. But this thing here is more powerful in the sense that it contains all light cones. How? Well, we pick a point here. We then slice the surface with the x equal to constant plane. And what we get, in fact, will be simply the light cone centered at the point we have chosen here, and vice versa. We can also do sections this way, and what we'll get will be again a light cone. So this object contains all possible light cones you can think of. So it's rather complicated, but in that sense, it contains a lot of information. Unfortunately, it's also quite complicated. It's a 7-dimensional submanifold, and actually not a properly immersed submanifold in an 8-dimensional space. So it's not globally an immersed submanifold of dimension 7, but locally we can hope it is. And I will assume that this is true at least in the vicinity of the points O and E. I guess you can simply, this is simply true. I cannot prove it, but I suspect that this is simply true if we make sure that O and E are far away from any kind of caustics. Okay, so we've got this complicated surface, local surface of communication here. And we look at it at a small neighborhood around the points O and E. Now, if you have a surface, a hypersurface of codimension 1 in a big manifold. Yes.
So locally about this 7-dimensional variety or whatever, you may think that I take a small neighborhood in space-time and I draw local cones from any point, and the collection of cones, the usual sum, just
it's more complicated. It's more like shapes of cones centered here, what they look like right there, and vice versa. We will get to that. It's a little bit more complicated than that. If you take this surface in the vicinity of OE, then by choosing a point here in the vicinity of O and looking what you get here, you will see the light cone corresponding to the point right here, what it looks like far away at near E, and vice versa. If you pick a point in E, take the appropriate section, what you will see will be the light cone with the vertex right here, but seen on the other side. So it's a bit like, by restricting myself to the neighborhood of these 2 points O and E, what I will see will be what the light cones centered here look like over there, and vice versa. That's how it works. But the thing is that I assume that this is basically at least locally a submanifold. And if you have a submanifold, you can always approximate its shape. And the way to approximate its shape in differential geometry is to give the normal vector, which defines the tangent space at the point OE. And if you want to be more precise, you add the curvature corrections. So you add the extrinsic curvature, which defines how it is locally bent. And hopefully you can also do it with the local surface of communication. And now comes the interesting part. In fact, it's very easy to find the equation for the normal vector. Basically, you take these 2 vectors, you take this now connecting geodesic, you take the tangent vectors LO and LE, you lower the indices, and here you've got the normal vector. Or precisely the normal 1 form. Now the extrinsic curvature, it is given, strictly speaking, by the distance between these points plus the curvature corrections here. I will later show exactly how. This is a bit complicated, but in the end, you can express it as a function of curvature along the line of sight. And let me also note that these things are not normalized. L is null with respect to the given metric, so you can always rescale these two objects by any number. The proof that it is so goes through something called the Synge's world function formalism. defined by Synge for his, in order to study basically geodesics in any space-time. A couple of years ago, 3 French physicists used it for exactly for investigating times of arrival of signals in the solar system. So the idea I'm using here is not completely new, but this geometric interpretation is new. Okay, so let me go further. So how do you get this extrinsic curvature or U from the curvature tensor? I promise that. Well, the idea is to take the resolvent of the geodesic deviation equation along this node geodesic. So the geodesic deviation equation along the geodesic is a second order equation. If you give the initial value and the value of the initial derivative of the solution, you should be able to recover it everywhere. And since it's linear, the solution at any point is a linear function of the solution of the initial data. And what gives the mapping between the initial data and the solution at the given point is exactly this big matrix W, and it satisfies the resolvent equation, which contains the curvature. This equation is here written in some kind of parallel propagated frame. I don't care what it looks like. So basically, initially it has to be a unit matrix, and then in the mean, and here you have a matrix made of unit matrix and the curvature tensor. This is, by the way, exactly the evolution equation in quantum mechanics minus I times h here. So you can think that the curvature is a kind of small perturbation. That this is basically the Hamiltonian. This matrix with a 0 would be then the free evolution Hamiltonian, and this would be a kind of time-dependent perturbation. Okay, so we get this W. What can we do with that? Well, we can define a symmetric 2 tensor on TOMM by taking all the 4 submatrices of W and arranging them in this particular way. It looks quite abstract and strange, but I will later tell you where this comes from. GO is the metric at all, and then you have this thing here. And you can show that the resulting U defines a tensor in the tangent space to OE in the product manifold. And this tensor is also quite curiously always symmetric. It's very non-obvious from this formula, but it's true. And now how do you get the extrinsic curvature? Well, you simply restrict this tensor here to the space normal to L. And there you go, you define the shape of the local surface of commutation.
X and L.
X and L?
Yeah, this kind of
okay, so this is
coordinate.
Okay, here's how it works. These are parts of the resolvent. So the resolvent, let me. So this formula here defines an 8x8 matrix, which naturally decomposes into 4 4x4 matrices.
Yeah,
Physically, they correspond. If you solve the geodesic deviation equation, I will write it on the blackboard. So imagine that you solve the geodesic deviation equation. Okay, so we try to solve the geodesic deviation equation along this curve. With some kind of initial data. Let's call it psi O of alpha, and with the first derivative. And then the solution at a different point, let's say lambda, will look like this. So strictly speaking, these are all bitensors. They take you from, these are all bitensors. They take you from the tangent space here to the tangent space over there. And physically, WXX and WXL tell you how the initial data correspond to the value of the solution at point E or any other point. LX and LL tell you how they correspond to the value of the derivative at this point. So this is called resolvent. You have to, this is a second order ODE, but you can write it formally as a first order ODE by enlarging the space of solution formally to a bigger vector, and then you look for the resolvent.
Czyli X odpowiada Xi, a L odpowiada pochodnej.
Tak. Tak, o to. Okay. So I think this should be no. Okay. So okay, I will tell you this may look very abstract and strange, and you may wonder where all these results come from. So they come from the Synge's world function. So let me tell a few words about this thing. It's a very interesting topic in GR. Not many people have heard about it. It's a very old tool dating back to 1960s, and apparently Synge was inspired by even earlier papers by, I think, Hadamard. So Synge's world function is a very useful gadget. It's basically a biscalar, so a function which takes 2 points in the given manifold. Let's say in a neighborhood in the product manifold, and it has real values. It's most easily defined in the local convex neighborhood where there is only one geodesic through a given pair of points. If there is more, then there is a bit of ambiguity here. So let's assume we are in the that there is only one geodesic passing through each pair of points. Then we define sigma to be basically the integral over the only connecting geodesic of this thing here. Lambda 1 is the value of the parameter corresponding to x prime. Lambda 2 corresponds to lambda. So we integrate the product of the tangent vector from lambda 1 to lambda 2, and we will scale it with this difference here. It doesn't, this looks a bit, actually, when you see this definition for the first time, you may think that this is something very stupid because, well, this is a constant, so you can just take this constant outside and that's it. But the interesting thing comes when you calculate the properties of that. Namely, if you take the derivative of sigma with respect to the unprimed x, what you get is basically the value of the tangent vector at the point x with the index lowered and with some kind of prefactor here. And the same on the other side. So you get the value of the tangent vector here. And how is it helpful? Well, very simple. In a curved space-time, it's sometimes very difficult to predict which 2 points, where you are supposed to shoot your geodesic in order to hit a particular point. And if you have got the world function, this becomes an easy problem because you just calculate the derivative with respect to x prime for this particular pair of points, and you get basically the right vector with lowered indices. And the same on the other side. So it's like a potential for solving the geodesic problem. That's one. And from that, you can show also that its higher derivatives satisfy very interesting properties. A small problem is that it's pretty difficult to calculate this thing in practice. So people haven't used Synge's world function very much unless they're working in certain particular problems, like, for example, the problem of motion of a body of a finite size or things like that. But there's another interesting property, which I will explore here, namely, it's easy to see that sigma is positive if the connecting geodesic is spaceline, is 0 when it is null, and it's negative when this is a time-like geodesic. It's pretty obvious to see from here. Okay. And this property means that simply this local surface of communication can be identified with the 0 level set of sigma. So if you want to identify when a signal sent from here will hit there, you have to look at the 0 of this Synge's world function. Okay, and now comes the original part. So my idea was to expand the Synge's world function up to the second order near the points O and E connected by a null geodesic. And I do it in locally flat, in a coordinate system which is locally flat around E and around O. And in that case, you get simply, there is no 0 order term because sigma EO vanishes. They're connected by null geodesic. There's a first order term, and there are quadratic terms, and I neglect the third order. And since these are locally flat coordinates in O and E, I can safely use covariant derivatives here instead of standard ones. It doesn't make any difference. So it's now very easy to see that the condition that this is supposed to vanish looks simply like that. L times x plus half u x is equal to 0. Well, x is basically the vector made of deviations on both sides. L is simply the vector made of first derivatives of sigma, and they're just related, as we noticed, to the tangent vectors. And u is basically the Hessian of this world function in m times m, with a rescaling, but you can always rescale this L and u the way you want. Now we have to look at this thing here, how it is related to curvature. Well, you can relate it to the curvature if you notice something very interesting. So this Hessian of the world function, it is very well known. It gives basically the relation between small displacements of the initial point of a geodesic here and there, delta xo, delta xe, and the variations of the tangent vectors here and there, delta lo and delta le. So if you imagine that you hold with your fingers your geodesic as like a string here and there, and you slightly vary the endpoints, the variations of the tangent vectors will be given by u times these things here. It's in this, I think it's also in the Synge's textbook. But you can also approach this problem of variations from the point of view of the geodesic deviation equation. So W gives you the relation between the initial variation of the endpoint of the geodesic and the variation of the initial tangent vector with the variation of the final point plus the initial of the tangent vector at the final point, right? That's from the definition of W. And now we just have to compare these two relations, and it's easy to see that you can pass from one to the other by not very simple, but also not very difficult algebra. If you parse this U and W into 4 submatrices, you can pass from one to the other, and you get the relation between the resolvent of the geodesic deviation equation and this matrix of second order derivatives of the world function. It looks a little ugly, but it's not that important. And since this is a Hessian, it has to be a symmetric matrix, actually. And interestingly, it turns out to be symmetric exactly because this matrix W is a symplectic matrix, and vice versa. Since it is symplectic, this turns out to be symmetric, but that's a different story. And this relation was partially known already from Dixon. Basically, what people knew was the upper part of this relation. So the relation between the WXX and WXL, which were known as, which people from this scientific community called Jacobi propagators, and the first two parts of the world function. The second, I've never seen the second row calculated, so it's probably new. And I think it's very useful to look at that from this global perspective of the whole resolvent and the whole matrix U. Okay, so now we've got the relations, but how does it apply to the problem of times of arrival exactly? So I assume that along this null geodesic, I introduce two orthonormal tetrads. UO will be the for velocity, and we have 3 spatial vectors. They can be anything. We have UE on the emitter side, and again, any 3 special vectors. I don't care what they are. I assume that they are both properly oriented, but nothing more. And this defines locally flat coordinate systems near E and O. So I can now identify points very close to E and O with tangent vectors at TO and TE, TOM and TEM, respectively. Also, this gives me locally flat coordinate systems in the product manifold simply by taking the product of the two maps near E and O. And now what I can do, I make a gauge choice that L0 is equal to 1. Remember that these vectors L and U are always given up to any rescaling you can make. So I can make this choice. And now what I want to do is to calculate X0 with respect to other things, which is basically the time the clocks here read when they obtain a signal from a point located x1, so the first three coordinates will then label the position from which, the coordinates x5, x4, x5, and x6 will label the position of the emitting clock. X7 will, I think, map the time of emission, and x1, x2, and x3 will correspond to the position of the observing clock. Both of them.
What do you mean by locally flat coordinate system?
It can be, for example, Riemann's normal coordinate system.
Because this is just a coordinate system which comes from the tangent space.
Yeah.
At one point, but why you call this coordinate system locally flat?
Because the gammas, the Christoffel symbols vanish at these 2 points, and that's all.
That means no target.
Okay, it's not locally flat. It's
This is a special coordinate.
yeah, it's a special coordinate system with vanishing gammas.
Locally flat, it's insane.
Okay, locally Minkowski, locally inertial. Okay, so here, yeah, locally inertial frames. Yeah, I can.
Local inertia is fine.
Yeah. So those would be 2 local inertial frames here with locally inertial coordinate systems. So now you can express the time of arrival as registered by a clock by the position of that clock, the position of the emitting clock, and the time of emission, which is x7. And that's exactly expressing x0 with 7 other variables. And when solving the equations from the previous part, what you get here is that x0 is Lixi. This is the 7 coordinates here. And then you've got a quadratic term given by sub q. And this q is nothing else but the extrinsic curvature expressed in appropriate coordinate system here. So when you calculate everything from the previous in a particular coordinate system, you get exactly the time of arrival in terms of the displacements and the quadratic term, which is given by u. Okay. Now, this is interesting, but what is also interesting is the inverse problem. So imagine that we have managed to measure a sample of times of arrivals between various points. So in other words, we have a lot of points in m times m, which we know that correspond to pairs of points connected by an L geodesic. And we imagine we've got a lot of them. Using this data, can we reconstruct L and U? The answer is yes, because that's basically the geometric problem of finding a quadric through a given set of points. And this is known that it is solvable under certain subtle assumptions. I don't want to go into that. But the idea is simply that if we have a number of pairs of points for which we have measured, for which we know that they're connected by null geodesics, we can now treat Li and Qij, the values of this form L and the extrinsic curvature, as the components of the normal vector and extrinsic curvature, and we solve for them by knowing a number of points which satisfy these conditions. And this is a linear system of equations, so formally there shouldn't be any problem, because this is basically finding a quadric, actually a special type of quadric for a given set of points. And this is a very classical problem in algebraic geometry, except that here we have a rather high dimension of that. This is possible, but you have to make sure that the sampling is done right. If you do your sampling in a stupid way, for example, all points lying on one line, you won't be able to probe the curvature in some directions. I tried to figure out the exact condition for the sampling being done right, but this is rather complicated. However, at least I'm able to provide certain way of sampling which certainly works. I will tell about this later. So that's basically determining the shape of the local surface of communication in the sense of the components of these guys from the variations of times of arrival between many pairs of points. But how should this help us with measuring curvature? Well, let's look at this U part. In a flat spacetime, you can easily show that you can find a diagonalizing basis for that. And in this basis, this is an extremely simple tensor. This is degenerate in 5 out of 7 directions, and in the other 2, it's basically diagonal with the same eigenvalue. However, in a curved spacetime, well, you can always show that this must be degenerate in 2 directions, but there is no restrictions on this 5 by 5 matrix. So there is potentially a way to see the curvature corrections on top of finite distance effects, because algebraically speaking, this is a different type of tensor. They have different shapes, so to say. So curvature causes changes of the shape of the local surface of communication, and we need to detect this imprint of curvature. Now, the problem is that it's very difficult to have any control over the orthonormal tetrads we use in the 2 systems. So the idea is now to look for 2-sided Lorentz invariants, so some quantities which don't depend on the choice of tetrads on both endpoints. And here I decided to use something from our previous papers, something I call the distance slip. Roughly speaking, you can define this quantity in a couple of ways. One of them is to think of a congruence of null geodesics, which is initially parallel at O. You take the cross-sectional area of this congruence, you follow backwards in time, and at some other point E, you get a different value of area, and you calculate this coefficient here. So in a flat spacetime, this is certainly 0. In a non-flat spacetime, these geodesics undergo certain focusing, and you can see it by non-vanishing value of mu. The funny thing is that this quantity is independent of the states of motion of both the observer, which calculates this value at O, and the observer which calculates at E. It vanishes in a flat spacetime, and for short distances, you can show that it's an integral of the stress energy tensor. You can also find an analogous quantity where the congruence is initially parallel at E, and again you get a scalar quantity measuring the impact of curvature sort of in the other direction. We got interested in mu because we realized that actually mu can be measured in a different way. You can do it by comparing the parallax distance to a given body with the angular diameter distance. So there's a couple of ways to measure the distance between a light source and an observer. One of them is the definition by the angular diameter distance. We assume we know the cross-sectional area, physical cross-sectional area of the body, and we compare it with the stereographic angle it takes up on observer's sky. This way you get the angular diameter distance. There is also the luminosity distance related to the previous one. But you can also think about measuring this distance by parallax. And in a flat spacetime, this is simple. Basically, the parallax angle is inversely proportional to the distance. In a general spacetime, you've got a linear map here, but you can define a baseline average quantity by taking the determinant. And the funny thing is that mu can also be calculated as the difference between the 2 distance measures. Strictly speaking, there is a plus minus here, which can appear when we pass through a focal point or a caustic, but I don't care about it at the moment. This happens for very long distances. For short distances, this is basically the difference between the angular diameter distance and the parallax distance between a given source and observer. That's how I got interested in this quantity. Now the idea here is to express these quantities using using L and Q. Is it possible? Actually, it is. It takes a bit of messy algebra, but if you take the spatial antisymmetric tensor epsilon in both endpoints, you take the components of L and Q, you can show that something like this happens. So we can express mu and nu using the various parts of Q and various components of the vector L. So we have shown that mu depends on the on this extrinsic curvature of the local surface of communication, the normal vector to it, and also on the local, but formally it also depends on the frames we have chosen here, UO and UE, because we're explicitly using coordinates here. However, using a little bit of messy algebra, you can show that in fact there is no dependence here. It's not trivial because here I'm using only spatial part of the indices, so it's not explicitly Lorentz invariant in either of O and E, but in practice it is. It takes us some time to prove that. So no matter how we have arranged our coordinate system here and there, we'll get the same value of mu and mu. Expanding in the powers of curvature, it's possible to show that this mu and mu are integrals of the stress energy tensor contracted with L and with linear kernels, one of them vanishing at the observation point, the other one vanishing at the emission point. At the leading order, the Weil and lambda drop out. This is a bit abstract, so let's now assume some kind of matter model. We assume that we have pressureless dust and very weak gravity. In that case, mu is given by the integral of the mass density profile along the line of sight with this type of kernel here. Mu is given also by the integral of the mass density profile with this kernel right here. And using these relations, we can pass to a bit more physical quantities, for example, the average matter density along the line of sight. If we know the distance between these 2 points, then we can express the average mass density using mu and mu. And another quantity we can express is the first moment, or for example, the position of the center of mass of this mass density profile. So basically, the first 2 moments of the density profile along the line of sight is something we can express using mu, nu, and the distance between these 2 points. Okay, that was very abstract, but can you really design a measurement protocol? Actually, it is possible. The setup we propose here consists of 13 clocks, one somewhere in the middle, other 12 located, as you can see on in this picture. So in the autonomous coordinates, both the emitting and the observing ensemble have this particular shape with some size L. The emitters emit signals at 3 moments at the local time on the emitter side minus L over C0 and L over C. And now this arrangement has a very nice property, namely, you can derive exact expressions for the components of L and Q from the times of arrival here. This is because the geometric structure, this is because of the geometry of this thing here. You can use various tricks. For example, the fact that the components of L and Q behave differently under the reflections of spatial coordinates, or you can use the polarization theorem. And in the end, you can arrive at reasonable, exact expressions for L and Q in terms of the times of arrival. So if you sample your times of arrival exactly according to this protocol, you can certainly invert the relations between the measured times of arrival and the components here. Note that there is here, I assume that we measure the times of arrival between any emitter and any observer. So you've got 13 times 13 numbers, although not all of them are actually used. Times 3, because this ensemble actually has to emit signals 3 times. Okay, is the signal large or small? Unfortunately, it's usually very small. So let's make a number of assumptions. I assume that the size of these 2 ensembles is L, which is much smaller than the distance between them, D, which is on the other hand much smaller than the curvature radius. Then we can introduce dimensional as variables. We can explicitly write down the equation for the local surface of communication, including the so-called flat space-time or finite distance effects, and on top of that, the curvature effects. And you can really see that there is a hierarchy here. This thing here, which is responsible for the redshift and the Raman delays, is by far the largest. Then the finite distance effects are suppressed by the inverse L divided by the distance, L over D, kind of expected. Finite distance effects are suppressed by the size divided by distance. And the curvature effects are small on top of that because they're also suppressed by the distance divided by the radius squared. So we assume that we have some kind of constant mass density here. This gives the curvature scale. And now what is the size of the signal? There is a very simple rule of thumb. So let's measure the mass contained in a narrow cylinder, which connects these 2 points, which has size d and radius L, corresponding to the size of the emitting and receiving apparatus. Then we calculate the Schwarzschild radius corresponding to this mass, and we divide it by c. So we take, let's say, the crossing time of photon of the Schwarzschild radius, and that's basically the size of the curvature corrections. This is a small effect. For example, if between O and D you have the whole Jupiter's mass, then the curvature correction will be 10 nanoseconds. If this is one solar mass, then it will be about 10 microseconds. So the problem is that gravity is weak, so these corrections due to curvature are always fairly small. Okay. So that's where I will probably finish. Here's the summary. So if you calculate the variations of times of arrival of the second order between 2 distance regions of space-time, then you can measure the curvature, then the signal will contain curvature corrections on top of finite distance effects. And the reason is that there is a geometric relation between the extrinsic curvature of the local surface of communication at a given pair of points and the space-time curvature along the node geodesic connecting them. And it's possible to extract, nevertheless, this curvature effect by a clever differential measurement, which kills all the first order effects and also all the finite distance effects. And on top of that, kills also all the geometric effects due to the rotation and angular position of your apparatus, or due to the for velocity or proper motions of your apparatuses as well. So only curvature. It's funny because only curvature contributes here. From that, it's possible to obtain the first 2 moments of mass distribution along the line of sight. And this is a differential measurement. The curvature effects are shielded from much larger contributions like the tidal forces of massive bodies flying around, the effects of misalignment or the angular position of both the receiver and the emitter, or the difference of their velocity. However, the effects are usually very small. Does it have any applications? I don't know. One place where this might have applications would be binary pulsar timing, because there, in this particular situation, you indeed have 2 bodies, possibly on a complicated elliptic orbit, which sample the times of arrival from rather complicated over a rather complicated shape. However, here the signal is mixed with many other effects, and you would have to see it on top of many other things. But if I would look for any kind of applications of all of that, this is where I would look first. Okay, and that's it. Thank you.
Some questions, perhaps? Maybe people online have some questions, if you hear me. I have a question. So, to have some intuition, what do you have to know about sources to measure, to make some conclusions? Yeah?
Well, you have to know the positions and moments of emission of these signals in some kind of local inertial frame. But it doesn't matter which frame. You don't have to know that frame, but you have to know these positions in a inertial frame.
So using some other methods, you need positions of emitters, yeah?
That's right. Okay, so in binary pulsar timing, by doing a very clever fit involving many things, including the Shapiro delays, it is possible to fairly accurately determine the orbit of a binary pulsar system. And in that sense, if you're able to do it, then I guess you're done. However, you would have to see the effects of light propagation on very on top of many other effects. But you have to know the positions in some kind of coordinate system, inertial coordinate system of the emitter.
And identify the signal. Yeah?
Yes. So this particular measurement demands a lot. On the other hand, it's the one which is completely shielded from any other effects. However, maybe you can make other compromises, measure other parts of curvature, and maybe with different protocols which are more feasible. I don't know. At the moment, this is one that I came up with. Obviously, if you have various properties of this second order of this extrinsic curvature of the local surface of communication, you can try to extract a lot of information from that. And maybe you don't need that much knowledge of the emitting system to get that. But I didn't think about it. It's a difficult problem actually.
Okay. Who else?
I have a remark that nanosecond and millisecond for our colleagues here in this building is a very long time. They managed to measure picoseconds. So for a big optics, it's a big time.
Yes, but these measurements are usually done in radio waves. In radio waves, and radio waves are prone to many problems with this type of time of arrival measurements. For example, they are not propagating, strictly speaking, in vacuum. So there will be refraction effects and other things. So not being an expert on that, I don't know how feasible it is to measure anything here. I'm just showing that there is a possibility here.
Who else? No? Okay, thank you again.
Thank you.